Okay, now we are on YouTube. Or if you are ready, you can start.
Okay, let me see if Xuhui is online already. Let me send him a message.
Yeah, Xuhui is now is he in quarantine?
Yeah, he's at home. Yeah, he has limited access.
So Xuhui just make a lecture recorded today. So we will use this alternative way to give this talk. But Xuhui will be online to ask any question in the Q&A session.
Yeah, I think we can get started right now. So I think Xuhui will join us very soon. So good morning, everyone. Welcome to the Complex Flow and Soft Matter seminar. So today we are going to talk about a very hot topic nowadays. It's about the uncertainty quantification for the machine learning models. So to do that, we are very glad to have a leading researcher in this area, Dr. Xuhui Meng, to join us. So Xuhui is currently an associate professor at the Huazhong University of Science and Technology. He also did his PhD at the same university, and after that, he went to Brown to work at the postdoc for 3 years, where he focused on developing a machine learning model, and especially uncertainty quantification on the machine learning model. So basically, he co-developed this very powerful machine learning library for solving a partial differential equation. He's one of our organizers, Dr. Lulu from UPenn. And also he developed this very useful and widely used multi-fidelity neural network. And recently he has summarized all his work on the UQ in the scientific machine learning to this very comprehensive review paper, which is more than 100 pages. So today he's going to talk about this, this topic, the UQ on the scientific machine learning. So, because of this very strict lockdown policy, a COVID lockdown policy in China, so currently Xuhui is quarantined at his hometown where he has limited access to the internet. So in order to have a very smooth presentation, he just video recorded his talk and sent it to me last night. So I'm going to play the video record right now, and Xuhui is going to join us later. So if you have any questions, and you can type the question in the chat box, or you can ask the question after the presentation. So I think without further ado, let's start rolling, and I'll start playing the video record.
When you share the screen, you need to share the audio.
Can everyone hear the audio?
No, we cannot hear the audio.
Yeah, right now.
Three approaches are developed to quantify uncertainty in PINNs and
okay, yeah, let's guess.
Today I will be talking about quantifying uncertainty in physics-informed neural networks for solving forward and inverse PDE problems with the noise data. Here is the outline. Our first shows the deep neural networks and the universal approximation theorem. And then I will introduce how to encode PDEs to deep neural networks to get PINNs, physics-informed neural networks. And I will also introduce 3 approaches developed to quantify uncertainty in PINNs and the summary. Here is the schematic of deep neural networks, which consists of an input layer and 1 or more hidden layers and the output layer. Each layer will have a certain number of neurons, and for laser collection between each two neurons. And the output of each layer is the linear compilation of its input and the weights and bias with nonlinear transformation, which is the activation function. And such a structure can be used to approximate any measurable function with any design degree of accuracy. And the convergence rate increases as the number of the hidden units grows. And in practice, we can define the following loss function to fit a function. For example, y star is the given data and y is the output of the neural network. We can then use the stochastic gradient descent to tune the weight and bias in the neural network to make the output of the neural network to fit given data. And here is an example of a function approximation using a deep neural network. And the target function is a discontinuous function. And on the left part, it's a low frequency function. And on its right, it's a high frequency function. The black solid line is the target function, and the red dots are the output of the neural network at different iterations. So I'll play the movie again. So as you can see, the output of the neural network first fit the mean of the function, and then the low frequency part, and finally the high frequency part. And in this plot, we also show the output of the neural network in the frequency domain, and it also shows the learning mode of the neural network is from a low frequency to the high frequency. And here is a schematic of PINNs. We first use the neural network to as a surrogate for the PDE, for the solution of the PDE. And we can use the automatic differentiation to express the derivatives in the PDEs. For the forward programs, you can define the following loss function. R here is the residual of the PDE, and UBC star and UIC star are the measurements for the boundary condition and also initial conditions. We can use the stochastic gradient descent to minimize the following loss function to make the neural network to fit to satisfy the PDE and also the given boundary condition and initial conditions. After training, the output of the neural network is approximation to the solution of the PDE. For inverse programs, we can also use the similar loss function. And in the inverse program, we will have some measurements on the solution to the PDE, and we also have some unknowns in the PDE. We would like to reconstruct the solution and also try to infer unknowns in the PDE. And here's the loss function of the inverse program. We also have the residual of the PDE and the mismatch between the given data and the output of the neural network. And if we have measurements on the boundary condition or initial condition, we can also include them in the loss function, but these two parts are not necessary. And as we can see, PINN is a unified framework for solving forward and inverse PDE programs. And we don't need any mesh to approximate the derivative because we use the automatic differentiation to express the derivatives in PINNs. Now let's go to Bayesian physics informed neural networks, which we call BPINNs. So first of all, we need to know why we need BPINNs. And PINN is an effective tool to solve the inverse problems in inverse PDE programs. Here is a simple example to show the performance of PINNs for solving inverse PDE programs. And in this equation, we assume that we have some measurements on F and also some measurements on U. And we would like to reconstruct F and U and also infer an unknown parameter K here. The exact value for K is 0.7. And this is the exact solution for this PDE. And in the first case, generally the measurements of F and U are noisy. And in the first case, we add a very small Gaussian noise to the measurements on both U and F. And the blue points are the training data for U and F. The black solid line is the exact solution, and the red dashed line is the prediction from PINNs. So as we can see, in the first case, the PINN predictions agree well with exact solution. And also an unknown parameter k here also agree very well with the exact solution. In the second case, we try to increase the noise in the training data. See, now we have 10% measurement noise in the training data for both U and F. And as we can see, we got overfitting prediction for F. And the prediction for PINN. Also, predictions for PINN are the predictions for U from PINNs are also not as good as in the first case. And the inferred key here also we also have a very large error in the prediction for key. And in the PINN predictions, we don't have any uncertainties. To prevent the overfitting issue in PINNs, and also try to quantify the uncertainties in the PINN predictions, we propose Bayesian physics-informed neural networks, which we call BPINs. And here's the schematic of BPINs. We first use Bayesian neural networks to as a surrogate for the solution. And similar to PINNs, we can use the automatic differentiation to express the derivatives in the PDEs. And F is the right-hand side of the PDE, and X is any operator in the PDEs. And B here is the boundary condition. And if we have measurements or observations on the solution or boundary condition F, we can try to solve the forward program and also inverse programs, just like in PINNs, with uncertainties. To quantify uncertainties, we can use the Bayes rule. P theta is the prior distribution of the weight and bias in Bayesian neural networks, and the second term is the likelihood of the data, and which depends on the noise of the measurement. And this term is the marginal likelihood, and this is the posteriori. Given the noise data, we can try to estimate the posteriori of the weight and bias, and then we can get the posteriori samples of the solution in a functional space. So to estimate the posteriori here, we can use Hamiltonian Monte Carlo or variational invariance. So in BPINs, each weight and bias is a distribution rather than a point estimation in PINs, and all data can be noisy. And in our founding computations, we assume that the measurement errors are Gaussian distributions. And the first test case is a function approximation case. This is a target function, and we assume that we have 32 noisy training data for U with a 10% measurement error. And here's the architecture of the Bayesian neural network we use. And this is the reference solution. And the dashed line is the predicted mean, and the zones and the translations or uncertainties. And we use 3 different methods to compute the posterior distribution in BNNs. The first one is Hamiltonian Monte Carlo HMC, and the second one is mean field variational invariance, and last one is a dropout. So as we can see, BN plus HMC can provide almost the same results as in the reference solution. In mean field variational invariance and dropout, the more efficient than HMC, but the accuracy are not as good as in HMC. For example, here, so in the zones we don't have any data, the uncertainties are large, and if we go further from the data, the uncertainty, the predicted uncertainty will also increase. But in further variational inference, you can see the uncertainty, predicted uncertainties are almost uniform. And we also try to increase the noise in the training data from 10% error to 10% to 50%. And here's the reference solution, and this is the predictions from BN plus HMC. So as we can see, the predicted mean, the computational errors between the predicted mean and the exact solution are bounded by the two standard deviations, and we don't have any overfitting in, even have a very large noise in the training data. And now we try to extend we try to use BPINs to solve a differentiation problem. And this is a 1D nonlinear Poisson equation, and we assume that we have some measurements on F, and we also have two measurements for the boundary condition of U, and we know exactly the exact values for lambda and also k. We try to get a solution using BPINs given noise measurements on both F and U. And here's the prediction from BPINs with here's the predictions from BPINs for U, and here's the prediction for prediction for F using BPINs. And the red dashed line is the predicted mean, and the further zones are the predicted uncertainty from BPINs. As we can see, the computational error from between the predicted mean and the exact solution is bounded by two standard deviations or the predicted uncertainties. And in BPINs with variational inference, the uncertainties are very uniform, and the uncertainties are still very large, even we have data for the boundary condition for U. And now we try to apply BPINs to solve an inverse problem. So in this program, which we assume that we have some measurements on F and U. We try to infer an unknown parameter k here, and lambda is a known constant, and we assume that we have 32 noise measurements on F and 8 noise measurements on U. So this is a prediction from BPINs for the predictions for U from BPINs, and this is the predicted mean and standard deviation or uncertainties for F. So in this case, computation error between the mean and standard between the mean and the exact solution are bounded by the predicted uncertainties, and also for F, the computation error between the mean and the exact value are also bounded by the two standard deviations. But in BPIN with variational inference or dropout, the predicted uncertainties are quite uniform, which is not very reasonable. And here's the predicted key with uncertainties. Two different cases. In the first case, we assume that the measurement error in the measurements is very small, and then we try to increase the noise in the data. And this is the predicted mean for k using BPIN with HMC. And this is the predicted mean and uncertainty from BPINs with HMC. So as you can see, in these two cases, the computational errors between k, the computational errors between the predicted mean and the exact value are bounded by the two standard deviations. But in the remaining methods, the results are not as accurate as in this one. So in the last case, we assume that we have 32 measurements on F and 8 measurements on U. In this case, we try to reduce the number of the measurements for U. See here, we only assume that we have 4 measurements on U, and all the measurements are on the left part. Even in this case, we don't have any data on the right part of U, but we can still provide very accurate prediction for U. And the red dashed line is a predicted mean, and the random zones and predicted uncertainties. So we can see the computational errors between the predicted mean and the standard deviations between the mean and the exact value for U are bounded by the predicted uncertainties. And here is the predicted unknown parameter in the PDE key. And this is a predicted mean, and this is a predicted uncertainty, and this is the exact value. As we can see, the computational error between the predicted mean and the exact value is also bounded by the predicted uncertainty. And in the second case, we try to employ BPINs to two-dimensional contaminant source identification. Say we have a river, and there are some contaminated sources in the river, but we don't know the exact locations for the contaminated sources. We only have some measurements on the concentration in the river, and now we try to to identify the locations of the contaminated sources given measurements on the concentration. And in this program, we use the following model to represent the sources, and we would like to infer the XCI here, which is the location of the source of the unknown source, given measurements on the solution U here, and this is the exact value for the sources, and this is this is the predictions from BPINs with HMC. So as you can see, only the BPINs with HMC can provide accurate prediction for all the sources. And we also extend the BPINs to estimate multi-fidelity data. So the idea is very simple. We first use a neural network to fit the low fidelity data, and we use a Bayesian neural network to learn the correlation between low fidelity and high fidelity data. If we would like to solve inverse PDE programs, we can also use the same ideas as in PINNs, say automatic differentiation to express the gradients, the derivatives in PDE programs to solve the inverse PDE programs. And the F and B are the same as in PINNs, the right-hand side and the boundary conditions. And here we can also use HMC to estimate the posteriori of the width and bias in Bayesian neural networks. And in the following computations, we also assume the measurement errors are Gaussian distributions. So in the first case, we try to predict the sea surface temperature in the Cape Cod Bay. So in this case, we have two types of data. The first one is from sunlight, which covers the whole region, but the resolution is very low. And the second type of data is from the stations, in situ measurements, which are very accurate, but we only have 14 stations. And now we try to assimilate both the satellite data and the in situ data to accurately predict the sea surface temperature for the polar bay. And here's the architecture we used to fit low fidelity and high fidelity data. And this is the predictions using from the multi-fidelity BNNs. And we just use 12 of the data we just use 12 of the data from the stations as the training data, and about 2 for validation. And this is the predicted mean from the multi-fidelity BNNs, and this is the predicted uncertainty from the multi-fidelity BNNs. As for comparison, we also try to provide the results with the multi-fidelity GP Gaussian process, unless it's a predicted mean, unless it's a predicted uncertainties. And this is a comparison between the multi-fidelity modeling and single-fidelity modeling. By single-fidelity modeling, I mean, we just use the high-fidelity data as a training data to get the predictions. So as you can see, both the multi-fidelity modeling, say multi-fidelity BNNs and multi-fidelity GP can provide the small structures of the temperature, but the single-fidelity modeling can only provide the very coarse structure of the temperature. And this is a prediction from the multi-fidelity BNNs to the validation location. As we can see, the predicted mean agree well with the real measurement, and the computational error between the predicted mean and the reference solution is bounded by the predicted uncertainty in both BPINs and multi-fidelity BNNs and multi-fidelity GP, although in single-fidelity BNNs. And we also noticed that so in the multi-fidelity GPs, we expect the uncertainty will increase when we get further from the source or the measurement. But in GP, the uncertainty is quite uniform in this area, and in the multi-fidelity BNNs we propose, the uncertainty will increase as we go further from the measurement source, which is more reasonable. And we can also use the multi-fidelity BNNs to we can also encode the PDEs to the multi-fidelity BNNs to get the multi-fidelity BPINs. And this is a 1D example. And in this case, we assume that we only have 3 high-fidelity measurements for U and 10 high-fidelity measurements for F. And this is low fidelity data. We try to use the multi-fidelity BPINs to assimilate both the low fidelity data and high fidelity data to get the predictions with uncertainties. And the target of this program is to infer an unknown parameter key and also reconstruct U and F given the multi-fidelity data here. So this is a predicted mean and the standard deviation or uncertainty if we only use 3 high fidelity measurements on U and 10 high fidelity measurements on F. As we can see, at some locations where we don't have data, the uncertainties are very large. So we can perform the active learning to reduce the predicted uncertainty. By active learning, I mean we can add more high fidelity data at locations where we have large predicted uncertainties. For example, here for U, we can add 1 more data here. And for F, we can add 1 more data here to reduce the predicted uncertainty. So this is the prediction with newly added data from the predicted uncertainties. And we can see the predicted means are more accurate than in the first case, and also the uncertainties get smaller. And here's the animation for the case for the same problem with active learning. So as we can see, if we add 1 more training data here, the predicted key will be closer and closer to the reference solution. And also we can tell the accuracy from the predicted uncertainties as we increase more and more training data, the predicted uncertainties in both U and F will get smaller and smaller. And the last one is new uncertainty quantification framework in deep learning using GANs. So to quantify uncertainties in solving PDE programs, we can use the following 2 methods. The first one is the Gaussian process regression, and the second one is the Bayesian PINNs or the BPINs we proposed. But in the Gaussian process regression, we can only use it to solve linear problems, and it cannot handle big data. In BPINNs, it can be used to solve nonlinear PDEs, but the posterior estimation is in a very high. But the posterior estimation is for the wizard bias in the neural networks, which is very high dimensional, and also in BNNs, the price is for the hyperparameters and not for the output of the neural network or in the functional space. Even we have a very simple distribution, prior distribution for the weight and biases, we still don't know what's the prior in the functional space. Recently, a paper proposed to learn the stochastic process using the generative adversarial networks. And this is the schematic of the neural network of the generative adversarial neural network with GANs. In this neural network, we will have a generator and also a discriminator. The generator takes X and C. Here is a simple distribution, like say uniform distribution or Gaussian distribution. And the output of the neural network is the stochastic process. After the training, we can use the generator to generate a stochastic process as the given data. And if we have PDEs, we can also use the automatic differentiation, just like in PINNs, to encode the PDE for the output of the generator to get the physics informed GANs or PI GANs. And the training of GANs is a two-step training. This is a loss function for training the generator, and this is the loss function for training the discriminator. After training the GANs, we'll get a stochastic process, which is from the generator. So basically, after training of GANs, we will construct a mapping from a sample of a very simple distribution to a sample of stochastic process. We call it because the stochastic process is in a functional space, so we can see we call it functional prior in the functional space. And so here's the schematic of the framework we proposed. We can first use the historical data. The historical data can be from a function specified function distribution, say a Gaussian distribution, or it can also be from simulations or experiments in the past. To train a GAN, to construct a mapping from a simple distribution to a stochastic process. And then if we have some new data, for a function in a stochastic process, we can try to compute we would like to compute the posterior of the in the functional space, because we already have a mapping from the sample of a simple Gaussian from a simple distribution to the stochastic process. Computing the posterior in the functional space is the equivalent with computation of the posterior in the input space or the simple distribution. Here we also use the Bayes rule to get a posterior distribution in the input space or the parameter space. And then after we get the posterior samples in the input space, we can feed it to the generator to get the posteriors in the functional space. And because like the neural network is very expressive, so the input simple distribution can be a very low dimensional distribution. And for the posterior estimation, we can also use the Hamiltonian Monte Carlo and normalizing flow. And here's a simple comparison between the new framework and the BPINNs. First, for the stochasticity, in the new framework, the stochasticity is from the new employees, and in the BPINNs or the BNNs, the stochasticity is from the weight bias, the weight bias, and because of the expressivity of the neural network, we can use a very low-dimensional employees. So we can, based on our experiences, so we can use the say 20 or to 100 dimensional Gaussian distribution to learn most of the stochastic processes. But in the BPINNs, in the BNNs, for example, most of the neural BNNs we used in our BPINN paper is 200 layers with 50 neurons per layer. And in this case, we have more than 2,000 dimensions in the posterior estimation dimension. But in the new framework, we can reduce the premise from 2,000 dimensions to simply dimensions. So in the first test case, we use a specified Gaussian distribution, Gaussian process as the prior, and this is the Gaussian process we used to learn the prior, and we randomly draw 10,000 samples from this stochastic process to train again to get the functional prior, and for each sample we use 30 equidistant points to resolve the function, and the input noise of the dimension of the input noise is 40 here. And after training the guys, we will get a functional prior, and we assume that we have 10 random points for a new f. And now we would like to reconstruct u based on the learned functional prior and also the new data here. And in the first case, we assume that the measurements with very small noise, and this is the results from Gaussian process regression, which will be the reference solution for the new framework. And this is a predicted mean and standard deviation or uncertainty from a new method. As we can see, the results from the new methods agree well with the Gaussian process regression or the reference solution. And in the second case, we try to increase the number of we try to increase the noise scale from 1% error to 10% error, and as we can see, the results from the new method also agree well with the reference solution. And now we try to test the effect of the input noise on the predicted accuracy in the new method. And this is the reference solution from Gaussian process regression. And this is the prediction from the new method with 40-dimension input noise. And this is the prediction from the new method with 20-dimension input noise. As we can see, the results with the 20-dimension input noise is very similar as in the case with 40-dimension input noise. And these two results agree well with the reference solution. And now we try to use the new method to solve the flow problem just like in PINNs. And in this case, we assume that we have some measurements on F and boundary conditions for U, and we try to solve this equation based on the noise measurements from F and U. And this is the exact solution for U. And we can then get exact solution for F based on the exact solution for U. And we assume that we have 10,000 samples of F from the past. We'll try to train again with the historical data on F to get the functional prior for F. And then if we have some new measurements for F, and we will use we'll get a posteriori. We can compute a posteriori for F based on the functional prior and also the new data. And this is the functional prior for F. And after learning the functional prior for F, we assume that we have 10 random points for F and 2 measurements for U as the boundary conditions. Now we'll try to solve this equation given new measurements on F and U. So as you can see, this is a predicted mean. The red dashed line is a predicted mean for F, and the field zones are predicted two standard deviations or uncertainty for F. And this is a predicted mean and uncertainties for U. As we can see, even here we don't have any data on F. We can still get very accurate predictions. This is because we use the historical data for F to learn a very informative prior. And we also present the results from BPINNs for comparison. Here we use 2 hidden layer with 50 neurons per layer in the BNNs. And this is the functional prior for F in the functional space. And this is the predicted mean and the uncertainties for F, and this is the predicted mean and uncertainties for U. So as you can see, the predicted uncertainties in BPINNs are much larger than the predictions in the new method. This is because we don't have any historical information for F in the BPINNs. So in the new method, because we have a very informative prior for F, we'll have very accurate predictions for U and F using only a few measurements for F and U. And in the second case, we try to solve an inverse problem using the new method. And this is the exact solution for the new case. And here key is a function of U. And we assume that we have historical data on F and key R here. We try to use the historical data on F and key R to learn a functional prior for F and key R. And after training of the guys, we'll have a very informative functional prior for both F and key R. And if we have some new measurements on F and U, we'll try to reconstruct F, U, and also try to infer the unknown field PR here. And in this case, we assume that we have 10 measurements on F and 2 measurements on U. And this is the functional prior for F and PR. And this is the prediction from the prediction from the new method, the mean and uncertainties. And this is the prediction for U and PR. So here, even we don't have any data on F, because we use the historical data on F to learn a very informative functional prior. We can still get very accurate predictions here. And for U, it's similar. Even we don't have any data on U here, because we already have a very informative functional prior for F and KR. We can still get very accurate predictions for U and KR. So in addition to PINNs, we can also use the new framework to quantify uncertainties in a newly developed neural network, which is used to learn an operator. We call it deep operator networks, or DeepONet. So this is a schematic of DeepONet. It has a branchlet and a trunklet. And the output of the DeepONet is the inner product of both the branchlet and trunklet. For example, here, we try to learn the operator from F to U. Operator from F to U, we first need to generate some data for different F and different pair data for F and U. And we use the pair data F and U to train a DeepONet. And the input of a branch data is the input is F, which is some discrete values to resolve the function. And the input of the trunk data is X, which is locations or coordinates for F and U. And after training of the DeepONet for any given F, we can get the solution of this this PD or ODE in just one forward pass. So as I mentioned in last slide, to train the DeepONet, we will need some pair data F and U. And if we view the different Fs for training a DeepONet as a stochastic process or a distribution over functions, we can also use the same F to train the same training data for training a DeepONet to train a GAN to learn a functional prior for F. After training of the GANs, we can combine the output of the generator with the input of the DeepONet to get two stochastic processes. The first one is for F, and the second one is for U. And then if we have some new measurements on U and F, we can then get an estimated posterior in the input space, and then we can fit the posterior samples in the input space to the generator and also DeepONet to get a posterior for both F and U. Quantifying uncertainties in both F and U. So in the first test case, we use a fractional diffusion reaction system, and the mapping of the DeepONet is from F, the right-hand side, and alpha to the solution U. And here we assume that alpha and F. Alpha is from this distribution, and F is from a Gaussian process. And we use 10,000 different samples of F and alpha to train a DeepONet, and also we use the same data to train a GAN to learn a functional prior for F and alpha. So after the training of the DeepONet and GANs, we assume that we have 10 measurements on F and 4 measurements on U. We try to reconstruct F, U, and also try to infer the fractional order alpha based on the given noise measurements. And this is a comparison between value functional prior for alpha. And this is the prediction from GANs, the predictions from the new method. And radiation is the predicted mean, and the field zones are the predicted uncertainties, and the blue points are training data for F and U. So as we can see, both the predictions from F and U agree well with the reference solution, and the computation errors between the predicted mean and the exact values are bounded by the two standard deviations. And this is the predicted fractional order with uncertainty. And this is the exact value for alpha. So as you can see, the computation error between the two between the predicted alpha and the exact alpha is also bounded by the predicted uncertainty. And we can also use the proposed framework to quantify the uncertainties for very high-dimensional programs. For example, here we use a Approximation case to show how to quantify the uncertainties in a 100-dimensional program. And this is the governing equation for the Approximation flow. H is the pressure, and the K is the permeability field. And generally, the permeability will be different for different Approximations. For example, the soil or the rocks. And here, we use a stochastic process to represent the probability field for different parts medias, different parts media. And F here is truncated KO expansion for the following Gaussian process, and we only keep the first 100 leading terms. And then we generate 30 different samples per key, and use the numerical solver to solve this equation to get a per data k and h to train a DeepONet. And after training of the DeepONet, once we have a new key field, we will get the pressure in just one forward pass. And we use the same data to train the we use the same data on key to train a gun. After training of the gun, we can combine the output of the gun with we can collect the output of the gun with the input of the DeepONet to get two stochastic process for k and h respectively. And once we have some new data on f and h, we can try to reconstruct both k and h based on the new data and also learned the function prior. And this is the exact solution for k and h, and this is the predicted mean for k and h, and this is the computational error between the mean and the standard and the reference solution, and this is the predicted uncertainties. So as you can see, the computational error between the mean and the reference solution is bounded by the two standard deviations. And recently, we also finished a review paper, certainly quantification in scientific machine learning. In this method, in this paper, we test almost 10 different certainty quantification methods in deep learning, and usually in PINNs, I try to use this method to solve the PDE problems combined with PINNs and also DeepONets. And to make the implementation more efficient, we also developed the open source package SciML. And in this package, we include all the testing methods in the UQ review paper. And now we're testing this package, and it will be released soon. And I will skip the summary, and thanks to all our collaborators. I'll stop here, and thank you for your attention.
Okay, so thank you everyone for staying with us. So I see Xuhui already joined us. So if you have any question on the talk, and you can start ask a question. Hi, Xuhui, how are you? You are muted.
Hi, I'm good. How are you?
Good. So
Xuhui, I have one question.
Yeah, sure.
So in your review paper, you discuss different methods, but among these methods, which one do you recommend in practice? I mean, so good accuracy and relative fast.
Actually, if you want to have a very good accuracy, you cannot get the results very fast. This is
always trade-off.
Yeah, it's a trade-off. So basically, for accuracy, I would recommend, say, BNN or GANs or the function prior plus HMC. And if you just want to get, say, uncertainty very quickly, so you can try to use, say, deep ensemble and also BM plus non-different dynamics and things like that. So, but yeah, so basically, it's very difficult to get a very accurate uncertainties. So I mean, it's not like just let's done training the deep neural networks, and yeah, it's always a trade-off. So
okay, thank you.
Yeah, sure.
Yeah. Any other questions or comments?
Oh, hi, Xuhui. This is Zhao Yan from University at Buffalo.
Hi.
Yeah, and thank you very much for the very interesting talk. So I'm just curious, how is the average simulation time for you to train, like to complete the whole like uncertainty quantification analysis? Like Lu mentioned previously, so you have a trade-off between the accuracy and the simulation time. But I'm just curious about the average like simulation time that you can complete the full maybe one case analysis.
So for now, we only test one-dimensional, two-dimensional programs. So for the one-dimensional programs, it depends on how many data you have. So for us, we just use for one-dimensional programs, the training data will be limited to say less than 100. So for the most expensive method, Hamiltonian Monte Carlo plus BNN or GANs, it will take say 2 to 5 minutes to sample from the posteriori for one-dimensional programs.
5 minutes.
Yeah, because this is just a one-dimensional program. And for two-dimensional programs, for HMC, it will take about say 10 to 15 minutes.
So it's just a single process simulation, right?
Yeah. And if you use so for HMC, it's if you want to use the HMC, I mean it's a compilation with BNN or GANs or functional prior. And you can also use some fully collected neural networks like deep ensemble or dropout to get the uncertainties. It's not very accurate, but it's very fast. And it's like just like training of the standard neural networks. You can for one-dimensional or two-dimensional problems, it will only take you say a few minutes on GPUs.
I see. So my second question is about your parameterization. So I noticed that for your inverse problem, so you can get a good prediction for some parameter in your PDEs, right? So, but all the cases you've shown here is just a single parameter. I'm wondering if we have multi like parameters, say 10 to even 20 parameters. Will this algorithm still work?
Yeah, sure. Yeah. So I didn't show the results, some results. So we have some examples in which we try to infer the unknown field or function in the PDEs in our BPIN paper or the functional prior paper. And we also have an example in the UK review paper. Maybe I can share my screen to show you. I just show one example in the functional prior in the slides for the functional priors. Infer the unknown field in the PDE.
Unknown field.
But in the BPIN, in the results for BPIN, I didn't show the case in which we try to infer the unknown field in the PDE. So, for example, here.
Okay.
So we assume we have some data on F and U. We try to reconstruct the whole entire F and U, and also the unknown field KR here. KR here is a function. So you can see here.
Okay, thank you very much.
Yeah, sure.
Oh, Xuhui, since we are on this page, I have a question. So what are those 10,000 samples of F and KR? Are those just random numbers that
So here to train a GAN, we need some historical data to learn the functional prior for F and KR. Here, I just assume that we have 10,000 historical data for F and KR. It can be viewed as the data, the simulation data or experiment data in the past. And now you have a new task. You have new data on it. You use the data in the past to train the GANs to get a functional prior. And if you have some new data on F and KR, you try to improve the performance of the model based on the historical data. This is the objective of the functional prior, or the objective of the functional prior here.
Okay. Okay, thanks. Okay, so any other questions or comments?
So Shuhui, you in the multi-fidelity modeling, you show the results with the multi-fidelity BNN and the multi-fidelity GP. The results is pretty similar. So then what's the difference when you use this to model the computer cost, or what's the difference there?
So in the multi-fidelity GP, you can only handle the linear correlation between the low fidelity and high fidelity data. But in the multi-fidelity BNNs, you can actually capture any linear or non-linear correlation between the low fidelity and high fidelity data. And also, if you try to use the multi-fidelity BNN or multi-fidelity GP to solve PDE problems, for the multi-fidelity GP, you can only use it to solve the linear PDEs. But in the multi-fidelity BNN, you can also use it to solve non-linear PDEs.
Okay.
So if the correlation between the low fidelity and high fidelity data is linear, you will get very similar results for these two methods.
Okay. Have you done any test on the GP for nonlinear problem? Is totally fail, or just the accuracy is not good?
In theory, you cannot use it for nonlinear problems because, say, if you have a nonlinear transformation for a Gaussian process, the output is actually not a Gaussian process, then you cannot get a posteriori in theory.
Okay, makes sense. Thank you.
Yeah, sure.
Okay, so are there any other questions? Okay, I think if there's no more questions, and we can thank the Shuhui again for joining us. Also, I want to mention that Shuhui also mentioned at the end of his slides, he's going to share this package. Actually, Shuhui has the opportunity to file a patent for this package, which can be potentially sold for millions of dollars. But he insists to make it public available so that all the researchers like us from different areas can get access to this package. So we really thank for him for this very kind conduct. So I think all the audience, you can follow the website of our complex flow seminar, and we are going to update the information of Shuhui's package. So if it's become available, so you can get access to it. So, and that's the end of this seminar. So everyone have a good rest of the day. So we'll see you same time next week.
Thank you. Bye.
Okay, bye.